Today we're going to talk about utility AI, which is essentially the calculation of how useful a given action is for an agent in your game based on various considerations and factors in the environment and information about the agent itself. We're going to build a system from the ground up so that we have a good understanding of what a utility AI is and how it works so that you can put utility AI to work in your own game as its own system, or use the concepts of utility AI that we're going to cover today to enhance your existing GOAP, behavior trees, or even improve simple state machines. Let's get into it. The concept of utility AI is fairly straightforward. In a traditional AI, I'd have my training dummy here is the enemy and the skeleton is my AI agent. When the training dummy comes within the sphere that the skeleton knows about, he should be immediately identified as an enemy and attacked, or we could run away or make some kind of decision, right? He's in or he's out. He's a threat or he's not. That's traditional AI. I'm just going to expand this sphere a little bit for the illustration. In utility AI, when the training dummy comes into about this range here, he's not a big threat. He's a threat. We know he's there, but he's not really doing anything. He's not close enough to hurt us. He comes closer and closer and closer. The threat becomes greater. So what utility AI is an actual mathematical calculation to determine how useful taking certain actions are based on factors that are happening in the environment and in the agent. So the closer the enemy is to the agent, the greater the threat, and that will influence the kind of actions that we take. Evaluating all of these considerations at runtime is what makes utility AI very powerful. So we're going to evaluate the usefulness of actions such as pick up more ammo, pick up that health item, run away from the enemy. That will all be based on multiple factors in the environment. How close is the ammunition to pick up? How close is that enemy to me? How much health do I have left? And so on. That, in a nutshell, is utility AI. Let's start with the consideration class. A consideration evaluates a specific factor like health or proximity to something else, and it determines how important it is for the AI's decision-making process. It's always going to evaluate and return a normalized float value, which will tell us how desirable or useful a specific factor is for the AI at any given moment. To evaluate a consideration, we're going to pass in a context, which will be what the agent knows about the world around it. Now that we've created our abstract base class for considerations, let's implement the simplest concrete consideration that we can, which is to evaluate a constant. Here, our evaluate method doesn't even care about the context. It's just going to return the value every time. Let's also add a create asset attribute here so that we can use this in the editor. Now let's quickly have a think about this context object. Now the context is like a mini blackboard that's just for this agent. It's just going to have information that pertains to this agent and what they know about the world. The first thing it should know about is its own brain, so we have a reference to itself. Now all of my agents are also going to have a navmesh agent component. They're also going to have a target. We'll keep that as a transform. They may or may not have a target at any given time. We're also going to build a sensor component for them so they can detect things around them and know things about the world. Also keep a mini Blackboard style dictionary here. We'll just organize it by string keywords to some object. So in our constructor, let's pass in a reference to the brain, which is the most important thing. I'm going to make sure that the brain is never going to be null here with a precondition check. Preconditions is a class that we wrote in an earlier video that just simplifies null checks and different kinds of state checks. So if the brain is not null, let's make sure we set the reference into our member variable. Now, the game object that has our brain should also have our navmesh agent and our sensor. We can use our utility method get or add to make sure that we have those components on that game object. Alternatively, if you know the components are there, you could just use get component. And then we can initialize our data dictionary. Actually, let's simplify this using the context menu. Let's just move this to the initializer. Now, all that's really left for this simple context object is let's add two public methods so that we can get and also set data using our dictionary. Okay, let's move on to the next building block that we need for a utility AI, and that is actions. An action represents a behavior the AI can perform, such as opening a door or picking up an item, and it's chosen based on its utility score calculated from considerations. Now, every action will be related to one consideration. Later in the video, we're going to look at composite considerations so that we can combine multiple considerations into one. In order to determine how useful this action is, we're going to make a method here, calculate utility. And what that's going to do is evaluate the consideration and give us back the score to pass to the brain to determine whether or not this action is useful to perform right now. If it is, we need another method here that will actually execute this action. Now, optionally, we might want another method here so that actions can actually perform some setup on their own. So I'm going to call this initialize. We'll pass in the context and we'll make it totally optional. We'll just have a do nothing method here, but if we want to override it in other actions, we can. I'm also going to add an optional target tag to each action so that the AI can prioritize actions based on the closest or most relevant target matching that tag in the environment. So now that we have our base action class, let's make a concrete action. And the simplest one that we can possibly make is an idle. An idle action doesn't have to do much. Let's override the execute method. Whenever we execute this action, let's just set the destination of the navmesh agent to be wherever the agent is right now. Let's add a create asset attribute and all done. The brain evaluates all possible actions, weighs their utilities, and decides which action to take at any given point in time. As discussed already, our brain is going to need a navmesh agent and a sensor. So each of our AI agents in the game will have a brain, and we're going to assign some actions to that brain that it's able to choose from. The brain will also create and maintain its own context of what it knows about the world. Let's have an awake method where we create a new context and we'll pass in a reference to this brain. And remember that we had an optional initialize method on every action. So let's iterate over all the actions in the list and call that initialize method, passing in our new context. And that's all the setup we have to do right now. I'm going to use the update method for decision making, although you could put this on a timer if you didn't want it to run every frame. So the update method will be responsible for doing all the logic. But before we do any logic, let's have a separate method where we just update the context. This will make sure that the information we have about the environment is up to date. For now, I'm just going to leave it empty. So let's come back up to the update method and start figuring out which action is actually the most useful for us to take right now. Let's set a best action equal to null. Let's also have a float that'll be our highest utility. Let's start with that as float.minValue. Now let's iterate over all of our actions. For each one, we're going to actually calculate the utility score for that action. If that utility score is greater than our highest utility, then we're going to set the highest utility as such, and we'll choose that as the best action, and then keep iterating. When we come out of the loop, we should have figured out which best action there was, if any. If it's not null, then we know we have something we can do. So here, we'll keep it nice and simple, and we'll just execute that best action. And that's really all we need to get our brain up and running. Also, while I'm thinking about it, I'm going to rename the action class to be AI action just to avoid any potential conflicts with system.action down the road. Now, let's have a look at the sensor class. We'll run the sensor using a sphere collider, anything inside the sphere collider we want to know about. Let's have a detection radius that we can set. I'll start it at 10. If our actions are looking for specific tags, let's keep a list of all of those here so we can report back on them easily. Then I want to keep a private list of everything that we know about that's inside of our sphere collider. And of course, let's keep a reference to the collider itself just so we can dynamically change it if we need to. In the start method, let's get that collider set up. So let's get a reference to it first with getComponent, and then let's set it as a trigger and make sure its radius is the one that we've defined. And that's the bare bones of a utility AI. Let's go back to Unity. Let's start by having a little look at the agent here. Now I've already added the components to the agent, and you can see the brain here has no actions yet. There's nothing going on. You can see I've already added the sensor, and all it has is a detection radius of 20. That's it. So what we need to do now is actually create scriptable object instances of considerations and actions. Now I've set up a little folder structure as well, and I've docked actions and considerations using vtabs for easy access here. Let's start with a consideration. Let's make a consideration that's a constant. I'll just call it idle consideration, and I'm going to give it a max value of 1. Remember, these are normalized between 0 and 1. We'll tweak this value in a little bit, but we only have one consideration right now. Let's make an action that will use that consideration. From the context menu, I'll create a new idle action, and I'm just going to call it idle. And then we need to set its consideration to be our idle consideration. And of course, it doesn't really need a target tag. We'll just leave that empty. Last thing to do is select the agent. We want to make sure that the brain has at least one action to perform. So let's drag idle into that list. Okay, sanity check. Let's hit play. Okay, well, the skeleton, that's our little AI agent, is definitely idling. If we take a closer look at the brain script, I've created a custom editor here that's going to show us what we're currently doing, what the action is, which is idle, and what the consideration is. So we can see here we've got a utility value of 1, maximum value, because the consideration is returning 1 all the time. In most scenarios, idle, of course, is not going to be the max. Let's turn it down to a more reasonable value. Let's say like a 0.2, 20%. That way, idle isn't 0, so it's better than doing nothing, right? Okay, so now that we have the absolute basics done, we need to talk about how this actually becomes useful. If we take a look at this from another angle, in most AI systems, what will happen is your AI target, let's say it's the training dummy here, he would come over this threshold and enter into the collider space, and suddenly you would be aware that there's an enemy there. But how dangerous is he when he's far away? Obviously, when he gets closer and closer and closer like this, he becomes more of a threat. And so that's where you start using considerations based on mathematical probability. So when he's out at the far edge, he's not a very big threat. That might only be a 0.1 or a 0.2. But when he's really close and in your face, then he's like a 0.9 or a 1. The same applies to this little health game object. If I move it closer to the agent and the agent has taken some damage and has low health, it might be of more utility for the agent to go and pick up that health item than it is to attack the enemy. So let's build our first consideration that actually uses math to evaluate how useful something is. So let's use a new type of consideration for this, a curve consideration. And instead of plotting a bunch of different points out, let's just make use of the animation curve class. And we're going to want to pull some information out of our context dictionary to plot against the curve. Remember, we can store any values in there, but if we're going to plot them against an animation curve, we should make sure to normalize them. So let's make an evaluate method that will get that data from the context using that context key. Then we'll evaluate that input value against the curve. That'll give us the utility value for this piece of data. I'm also going to add a reset method here that'll give us an initial curve that slopes from high up down to low. And what that'll do is, for example, if we were evaluating health and our health started at 0, it'll give us a very high rating, a very high utility that we should do something about that. But as the curve progresses and our health goes higher and higher and higher, it becomes less important. We're going to see that in an example shortly. Now, let's suppose that getting a health item is the most useful thing we can do at any point in time. Let's have an action that'll actually take us over to that health item. Let's create an initialize method. And in here, I want to add to our sensor the tag that's associated with this particular action. So if I'm looking for a health item, I'm going to want to find items tagged as health. So we'll pass that into the sensor to make sure it's going to find them. If we decide to execute this action, we're going to call the sensor again and get the closest target with that tag. If it comes back with nothing, then there's nothing to do. That should technically never happen though, because the utility score would be 0. However, if we do have a target, let's set the navmesh agent to go there. Let's add an attribute to the top of this class so we can make it in Unity, and let's move on. So far, our sensor class has just been a placeholder, but we need to start dealing with those triggers so we know what's inside of the sensor. We're going to handle onTrigger enter, onTrigger exit, but both of these are very similar. So let's have a helper process trigger. That'll take in an action that we can run. In process trigger, we'll say, if this particular object that came into the trigger is untagged, then we won't care about it. Otherwise, let's iterate over all the tags that we know about, and we'll see if it actually is a match for the things we're looking for. If it is, we're going to run the action on them. So back in our trigger methods here, we can call the process trigger method, and on trigger enter, we're going to add into our detected objects, but on trigger exit, we're going to remove. Now there's one more thing, and that is during startup, there might actually be things within the trigger area. So let's do a physics overlap sphere here. For all of the colliders we find, we're going to do exactly the same thing. We'll call our helper method and add those objects in. If we come down to the bottom of the class, we had a get closest target method, and that was doing nothing at the moment. We're going to fill that out now. So what we want to do now, we have a list of all the objects in trigger range. If the list happens to be empty, we'll return null. Otherwise, let's get a variable here for the closest target and another one to calculate the closest distance squared. We'll set that to math.infinity. We can cache our transform position as well. Now we'll iterate over all of the objects that we know about. We've passed in the tag that we're looking for here, so let's compare the tag. If we found one that matches, let's figure out what the direction is. Let's figure out what the squared magnitude of that is. If it's closer to us than the closest distance we have stored in the variable, then we know we have a new closer object. Let's set those variables. When we come out of the loop, let's return our closest target. If we come back over to the brain, we're going to want to know a little bit about our health component in our context now. Let's store a reference to the health component that's on the agent. If we come all the way down to the bottom of the class where we had an empty update context method, in here, let's make sure that we're adding health into our context dictionary, and we'll pass in a normalized health value. So back here in the editor, let's create a new consideration, a new curve consideration. I'm going to call that health amount. So here we'll use the key lowercase health, and we'll evaluate that on the curve. Now let's make another action. The action is going to be a move to target, and I'll call this move to health. Now all of my health items here are tagged as capital H health, and we'll add in our health consideration. Finally, we just need to add our new action onto the agent brain and press play. I'm going to switch over to game view so I have access to these buttons that I've set up to quickly lower and raise the agent's health just so we can test this out. Now, I've already removed 10% of the health, and you can see our utility is 0.03. If I hit it again, it's now 0.1. And if I hit it again, the agent's going to move over to the health item because it's now determined that it's more useful to go and get that health item than it is to stand here idling. Now, I'm going to click that button a little bit more so we can continue to watch it go down. So one more click, it suddenly goes up to 35%. And if I click it several more times and almost out of health, you can see it's gone all the way up to 90%. And if I bring it all the way back up to full health, it's no longer useful to us to go and pick up a health item. So the utility is 0, and the agent has decided to start idling again. Now, we made that decision based entirely on the value of our health, but there are other factors that might play into this, like how far away is the health item? We might want to be able to combine multiple considerations together to make more intelligent decisions. So let's look at that next. So if we're going to combine considerations together, we should probably perform some kind of operation on them when we're combining them. So I'll list some kind of popular types here: average, multiply, and so on. Let's also have a Boolean here that says all must be non-zero. This could be optional, but I would say if one consideration evaluates at 0, it's probably not possible to complete the action. That might not always be true though, so let's keep it optional. Let's make it so we can choose the operation type in the editor. I'm going to default it at max. So we'll take whichever one of the considerations comes out with the highest value. And then let's have a list of all the considerations we want to combine together. In our evaluate method, first, let's make sure we actually have some considerations to evaluate. If we don't, let's return 0. Next, let's evaluate the very first consideration in the list and put it into result. After that, we can iterate over all of the other considerations in the list. Now, I'm going to make a suggestion here that you only use 2 considerations per composite consideration, and that's because you want to keep them small, easy to understand, and composable, because now you can start making composites of composites, almost like Lego bricks. So our for loop here is going to start at 1 instead of 0 because we've already evaluated the very first consideration. So now we can evaluate the next consideration. Let's say if that one evaluated to 0 and we've toggled the all must be non-zero flag, let's return 0. And actually, while I'm thinking about it, we should do that for the very first one as well. I'm going to scroll down and start a switch statement for our operator type here. Let's say for the first one, if it was average, assuming we only have 2, we could add them together and divide by 2. Otherwise, you're going to have to run some sort of aggregate. If it's multiply, we can just multiply the values together. I'll just paste the other ones in here because they're all self-explanatory. Now, once we're out of the switch operation and we've finished all the iterations of our loop, let's return our result as a clamped value. Now, before we jump back into Unity, I want to make one more consideration, and that is going to be a consideration to determine whether or not something is actually in range of us. It'll be a more complex form of the curve consideration. Now, the first thing I want to put in here is a max distance, and this is so we can have a little bit more flexibility than the entire range of the sensor. This should be smaller than the sensor size, but we might want to only consider things that are very close to us. Likewise, we might want to also consider an angle. So we might only want to consider enemies that are in front of us and not that we can't see behind us. This consideration will work with the sensor to find tagged game objects in the environment. Let's have a tag here. I'll default it to target, which I have on all my enemies. And just like the curve consideration, we'll evaluate utility based on an animation curve. Now, just like the curve consideration, I'll have a reset method here that'll give me a default animation curve. Now, in our evaluate method, just as a sanity check, let's make sure that this tag is already on the sensor. Our actions should have already put it there, but if it's not for some reason, we might as well add it in now. If you extend this system in the future, you might want to add an initialize method to all of your considerations the same way that we have for all of our actions. For now, we'll just keep it simple like this. So the first thing we're going to do is call that sensor and get the closest target so we can start making some choices. If the sensor can't find anything, then this has a 0 utility. Otherwise, let's cache our transform so we can be a little more concise. We're going to make use of a method from the Unity utils library in range of that lets us pass in a target transform, max distance, and max angle. Here again, we can say if it's not in range, then 0 utility. Now let's scroll down a little bit and we'll calculate the direction to our target. Using that, we can find the distance to the target. I'm just going to set the y to 0 on that and get the magnitude. Let's normalize that distance now. We know what the max distance of this consideration is, so we'll divide the distance to the target by the max distance. Now we can evaluate that against our curve and get the utility value. Let's pass that back. Okay, now we have two very powerful considerations. Let's go back into Unity and put them to work. So let's start here by making a few in-range considerations. I'll make the first one in range of health. That means I'm going to change the target tag to be health. Let's leave it at a 360 angle and 10 distance. That's good. Let's make another one that'll be in range of target so that we can find our enemies. So I'll rename it here in range of target, and the target tag is already correct, but I am going to change it to a 180 angle so that we can only find enemies that are actually in front of the agent. Next, let's make a composite consideration because I want to make a more complex evaluation of whether we should heal or not. I'll just call this one should heal, and we already have the other considerations that I want to use. One was to consider our actual health value, and the other one was to consider whether or not we're in range of a health item. For this one, I'll keep the operation type at max, but let's leave it so that they both must be non-zero. Now, if I come back to our move to health action, let's change the consideration to now use our composite should heal consideration. Let's make one more action to test out our enemy detection. I'll call this move to enemy. We'll add the consideration in range of target, and let's set our target tag here also to be target. This will let us test out how the agent reacts when I move around the training dummy in the scene. So last thing, we got to make sure that our new move to enemy action is actually part of our brain. So now our brain has 3 actions to evaluate. Let's press play and try this out. So for starters here, both the health item and the training dummy are actually outside of that 10 radius. Let's move the health item just a little bit closer and watch that value inch up. So there's a 0.01, let's move it closer, 0.07. So it's right at the bottom of the curve there, pretty much exactly 10 away. If I bring the training dummy right up behind the agent, the utility is still 0 because the agent is only detecting targets and 180 degrees ahead. If I grab the training dummy and bring him around to the front a little bit, we'll get a reaction right away. And depending on the curve, it has to be greater than the utility of idle, which was 0.2. But if I inch the dummy just a little bit closer, keep an eye on the values there, we'll see that suddenly, as soon as it gets just a little bit higher here, we're at 0.02 now, and a little bit closer, there's 0.15, just a little closer, and we'll be over that 0.2. There we go. So at that point, the training dummy now has a greater utility than the idle. If I pull the training dummy right out of here, then the utility of following the training dummy around goes back to 0, and the agent will choose idle, which has the highest utility at that point. But let's jump into game view, and I'll drop the health down a little bit, and let's evaluate this composite consideration. If we take a look there, we are in range of the health item. It has some value, but again, until one of those maxes out to be greater than idle, he's not going to go for the healing item. So once we drop the health down enough so that that utility goes over 0.2, then he'll decide, yeah, okay, now it's worthwhile for me to go and pick up that health item, and he'll get out of idle. And if I bring the health back up, of course, he'll go back into idle mode. So using that composite consideration, you can actually start to build up fairly complex considerations that use many, many different factors in your game to, handle everything from ammunition to whether I should attack an enemy or not, whether I should take cover or not. A few suggestions about that. If you are going to start making fairly complex structures, it's a really good idea to draw them out so you have a good sense of what's going on. And also keep in mind that the more complex you make these, the more tweaking you're going to have to do to get it perfect. The nice thing about keeping a composite small is that it's easy to use, but it's also reusable. So whether or not you have enough health to do something is a consideration that you can use in many decisions. One shortcoming of a basic utility AI like this is that it doesn't handle preconditions or chaining things together like you would get out of a GOP system. But what you can do is, if you understand the concepts of calculating considerations here, is you can take this concept and integrate it with a GOP system so that you have even smarter decision making. And the same applies to behavior trees, state machines, and so on. But that's not to say you can't build an entire game just using utility AI like this. Of course you can, and many games have been built that way. So I hope this video gave you some good insights into how utility AI works and gave you some ideas on how maybe you can integrate it into your game. Well, that's all I've got for you today, so I'm going to wrap it up. Don't forget to join us on Discord, hit subscribe and like if you haven't yet. I'll throw something up on the screen that was related to this video, maybe GOP or behavior trees, get you thinking more about AI for your game. Maybe I'll see you there.